guys, I hope you had a great week. Today we're going to be going over some Chapter 15 end of chapter questions. Chapter 15 introduces us to correlation in statistics, which is a technique that's used to measure and describe the relationship between two variables. In our calculations, we'll be able to measure three characteristics of the relationship between our x and y variables. The first is the direction of the relationship, whether it's positive or negative, the form of the relationship, whether it's a line or a curve, and the strength of the relationship, which is how closely our data points are together. Our first question asks us to calculate the sum of products of deviations for a list of x and y scores. They already tell us that both means are whole numbers, so we'll use the definitional formula for this calculation. The first step in our definitional formula is to calculate the mean of x and y. The mean of x is the sum of the x scores divided by the number of scores. So in this example, we'll add 4, 9, 3, 8, and 6 together and divide by 5. We'll come up with a mean of 6. Then we'll add our y scores together and divide by 5 because there are 5 scores, and find a mean of 5. The next step is to calculate how far each score deviates from the mean. So we'll calculate the value of the score and subtract the value of the mean. In this example, 4 minus 6 is negative 2, 9 minus 6 is 3, 3 minus 6 is negative 3, 8 minus 6 is 2, and 6 minus 6 is 0. Then we'll do the same with our y scores, subtracting our mean of y from each y score individually. Now we'll multiply each deviation of x with the corresponding deviation of y. So in this example, negative 2 times negative 2 would be 4. 3 times 0 is 0. Negative 3 times 1 is negative 3. 2 times negative 1 is negative 2. And 2 times 0 is 0. Finally, we'll add all of these products together to find the sum of products of deviations, or SP. And in this case, we get a value of negative 1. Our next question gives us a list of x and y scores. We are asked to graph a scatter plot with the 6 data points. We'll plot our x's on the horizontal axis and our y values on the vertical axis. This allows us to visualize the correlation and make an educated estimate as to the value of the Pearson correlation. In this example, we have a scatter plot that shows widely scattered points around a line sloping up and to the right. So we can guess that our value for the Pearson correlation will definitely be positive. But since the points are scattered widely instead of tightly around our line, we'll estimate that it has a weak positive relationship rather than a strong one, like positive 0.80 to positive 1.0. To find the sum of x, we will add up all of our x scores and come to a value of 43. We'll do the same with our y scores and come up with a value of 24. Since we're using the computational formula, we'll multiply each x score with its corresponding y score and then add those values together to give us the sum of x, y. And we'll come up with a value of 178. To find the sum of squares for x, we will square each x score individually and add them up and come up with a value of 327. Next, we'll do the same with our y-scores. We'll square them each individually and add them up. And we'll come up with a value of 108. To calculate the sum of squares for x, we'll take our sum of x squared and subtract the sum of x squared divided by n. We come up with a value of 18.83. To find the sum of squares for y, we'll do the same thing by taking the sum of y squared and subtracting the sum of y squared divided by n. And we'll come up with a value of 12. Next, we'll calculate the sum of products of deviations by taking the sum of the product of x and y and subtracting the sum of x times the sum of y divided by n. N in this case is not the total number of x and y scores, it's the total number of pairs of scores. And in this case, we come to a value of 6. We'll use our sum of products of deviations as well as our sum of squares to calculate the Pearson correlation, which measures both the degree and direction of the linear relationship between two variables. Our sum of products divided by the square root of the product of our sum of squares gives us an R value of 0.399. We can see when we calculate the mean of x that we don't get a whole number, and that's why the computational formula was best for this particular calculation. Our next question provides us with the Pearson correlations for 3 variables, x, y, and z, and asks us to calculate the partial correlation first between x and y holding z constant, then between x and z holding y constant. This calculation allows us to measure the relationship between 2 variables while holding the influence of a third variable constant. To find the partial correlation between x and y holding z constant, we'll take the correlation for x, y, and subtract the product of the correlation for x, z times y, z. Then we'll divide that by the square root of the product of 1 minus the correlation of x, z squared times 1 minus the correlation of y, z squared. So we'll square our correlation of x, z and subtract that value from 1. And we'll multiply that by our correlation for y, z squared subtracted from 1. We'll come up with a value of 0.833, which suggests a strong and positive correlation. The next section asks us to find the partial correlation between x and z holding y constant. So we'll take our same formula and just switch it around a bit. If you notice, our formula always takes the partial correlation that we want and subtracts and divides the correlations that include the variable that we're trying to hold constant. In this case, all of the correlations that include y, which we're holding constant, are included in the subtraction or division sections of the formula. So we'll take the correlation of x, z and subtract the correlation of the product of x, y, and y, z. We'll divide all that by the square root of 1 minus the correlation of x, y squared times 1 minus the correlation of y, z squared. We'll come up with a value of 0.658, which is positive but not strong, so it would be described as a weak relationship. Our next question provides us with a data table from a study measuring the relationship between cognitive ability and social rank for a group of birds. We are asked to use the Spearman correlation because social rank is an ordinal variable. And there are two situations where the Spearman correlation is appropriate to be used. The first is when the relationship between X and Y are measured on ordinal scales, or when the raw scores are on interval or ratio scales, but the form is not linear. The first step in measuring the Spearman correlation is to rank all of our scores from smallest to largest. We're going to include tied values in the list. I like to put a dot next to them so I know that I'm going to have to compute the mean of those ranked positions because the scores are tied. So these are the rank positions, but the final ranks will be the mean value of those scores. So in this case, 2 is at the rank position of 2, 3, and 4. So the mean of 2, 3, and 4 is 3. Likewise, the social rank of 3 is at the position of 5 and 6. So the mean of 5 and 6 is 5.5. The social rank of 5s are 8, 9, and 10 positions, and the mean is 9 for each of those. Now we're going to make these final ranks our X values and add them up to find the sum of X, and then we'll square them and add the squares to find the sum of X squared. Next, we'll rank our Y scores, which are the learning scores, and assign them a rank position based on their values from smallest to largest. For the scores that are tied, we'll compute the mean of the rank position and assign this value as the final rank for each score. These are going to be our Y values, so we'll add them up to find the sum of Y. Then we'll square each of our Y values and add them up to find the sum of Y squared. Next, we'll calculate the sum of squares for X by taking the sum of X squared and subtracting the sum of X squared divided by N. And we'll come up with a value of 78. Then we'll calculate the value for the sum of squares for Y by taking the sum of Y squared and subtracting the sum of Y squared divided by N. We'll come up with a value of 83.75. Next, we'll find the sum of XY by taking each X score and multiplying it by its corresponding Y score and adding them up. In this case, our X scores are our ranked social rank and our Y scores are ranked learning scores. We'll add them together and find the sum of XY to equal 379.5. We'll find our sum of products by taking the sum of XY and subtracting the sum of X times the sum of Y divided by N. And remember that N is the number of pairs, not the total number of scores. We'll come up with a value of 77 and use that to calculate our correlation by taking our sum of products and dividing it by the square root of the sum of squares for X multiplied by the sum of squares for Y. Our correlation of 0.953 is strong and positive. Next, we'll find what our critical value is by calculating our degrees of freedom, which is the number of pairs minus 2. We'll use these degrees of freedom to look up the critical values for the Pearson correlation in Table B6 of Appendix B in your text. When we look at the row for 8 degrees of freedom, in the column of an alpha level of 0.05 for a two-tailed test, we find that our critical correlation is 0.632. Since our R value is well above that, which would be in the tail, we will find that our results are significant for the correlation between social rank and learning ability. Well, that's it for this week. I hope these example problems help you perform the calculations for Chapter 15, end of chapter problems. I'll see you next time. Take care.